In recent months, whenever tensions in the Middle East rise, a nearly 200-kilometer sea route immediately becomes the center of global attention: the Suez Canal. If traffic through this corridor is disrupted, the journey between Europe and Asia can become thousands of kilometers longer, as ships are forced to sail all the way around the Cape of Good Hope at the southern tip of Africa. This shows that the artificial canal cutting across Egypt's desert is not just a transportation route, but a strategic artery of global trade for more than a century and a half. But to create a shipping corridor that now looks almost natural on the map, humans had to dig through a strip of land connecting two continents under conditions where there was almost nothing except sand and wind. So how was this massive project actually built? Join Mandarin Tech as we uncover the answer right now. Stretching more than 190 kilometers across the Egyptian desert, the Suez Canal is one of the most ambitious engineering projects ever built to reshape how the world moves across the oceans. Since it first opened in the 19th century, this artificial waterway has allowed ships to travel directly from the Mediterranean Sea to the Red Sea without having to sail around the entire continent of Africa, a detour that once added tens of thousands of kilometers to the journey. Today, around 18,000 ships pass through the canal each year, transporting nearly 700 million tons of cargo, including massive vessels up to 400 meters long and weighing as much as 240,000 tons. However, to keep up with the ever-growing size of the global commercial fleet, the canal has never truly been finished. Over more than 150 years of operation, it has been continuously deepened, widened, and restructured, from manual desert construction sites in the 19th century to a massive dredging project completed in just 1 year in the early 21st century. Looking at a map, many people assume the Suez Canal is simply a straight waterway cutting across the Egyptian desert, but in reality, its shape changed significantly during the massive expansion project between 2014 and 2015. In less than 12 months, Egypt excavated an additional parallel channel about 72 kilometers long along the northern section of the existing canal. The goal was not only to widen the canal, but to completely transform how ships move through the Suez route. Before the expansion, most of the canal still operated as a one-way transit corridor. Ship convoys had to take turns passing through and stop at designated waiting areas to allow traffic from the opposite direction to pass. As a result, the average waiting time could reach up to 11 hours, while the total transit time through the canal often approached 18 hours. After the parallel channel became operational, ships were able to travel in both directions simultaneously along a much longer stretch of the canal. This reduced the average waiting time to about 3 hours and shortened the total transit time to roughly 11 hours. To make this possible, dozens of high-capacity dredgers had to operate continuously in desert summer conditions exceeding 40 degrees Celsius, removing around 250 million cubic meters of material, while the original canal remained fully operational throughout construction. This is what turned the 2014 Suez expansion into one of the most complex construction while operating maritime engineering campaigns in modern history. To excavate a canal tens of kilometers long in less than a year, engineers could not rely on conventional land-based excavation methods. Instead, most of the work on the Suez construction site was carried out by a specialized fleet of dredging vessels known as cutter suction dredgers. At the front of each vessel is a rotating metal cutting head that continuously breaks up the soil and sediment on the canal bed. Immediately afterward, a high-capacity pumping system draws the mixture of water and loosened material into the vessel, creating a slurry that is transported through pipelines stretching several kilometers to disposal areas or land reclamation zones. Thanks to this method, the excavated material did not need to be transported by trucks like on a typical construction site. Instead, the entire volume of dredged soil was moved directly by water flow itself, allowing construction speed to increase significantly. In many sections of the Suez expansion project, the excavated material did not even leave the construction area. It was pumped directly to both sides of the canal, to form artificial embankments that helped widen the navigation corridor. In addition to cutter suction dredgers, trailing suction hopper dredgers were also used to remove material from the canal bed while moving continuously, then transport it to disposal sites located farther away from the construction zone. The coordination between multiple types of dredging vessels created a nearly uninterrupted construction workflow operating around the clock. Completing a project that was originally expected to take several years in just 12 months, while still keeping the canal fully operational, was one of the biggest engineering challenges of the 2014 Suez Canal expansion. Instead of shutting down the canal during construction, engineers had to organize the entire site so that construction and navigation could continue at the same time. Dredging vessels worked within tightly controlled zones to avoid interfering with commercial ships passing just nearby. Because of this, the maritime traffic coordination system had to operate with near-perfect precision to ensure safety for both shipping traffic and construction equipment. At the same time, the construction site was divided into multiple independent working sections so that dozens of dredging vessels could operate simultaneously. Rather than following the traditional step-by-step construction sequence, the project adopted a large-scale parallel construction model, allowing many segments of the new canal channel to be excavated at the same time. To maintain this pace, equipment had to operate around the clock under harsh desert conditions. During the day, crews worked in extreme heat and hot winds blowing from the Sinai Desert. At night, operations continued under massive construction lighting systems stretching across tens of kilometers along the canal corridor. If the 2014 Suez Canal expansion project was a modern engineering campaign supported by fleets of high-capacity dredging vessels operating continuously day and night, then the original construction site in 1859 began under conditions that are almost difficult to imagine by today's standards. When the first excavation work began, the region had no proper transportation routes for construction materials. There were no ports capable of receiving heavy equipment. There was no stable supply of fresh water to support a large workforce working for months under harsh conditions. Most importantly, there were no large mechanical excavation machines capable of cutting a canal nearly 200 kilometers long through constantly shifting desert terrain. Engineers at the time were attempting a task that had never been carried out before on such a scale. As a result, the early stages of construction relied almost entirely on manual labor. Workers used picks, shovels, and simple hand tools to dig through layers of sand. Excavated material was placed into small baskets and then carried away by hand or transported by animals such as donkeys and camels. Under extreme desert temperatures, strong hot winds, and limited shelter, excavation progressed very slowly and required enormous physical effort from thousands of laborers working continuously along construction zones stretching for dozens of kilometers. Fresh water quickly became one of the most serious challenges facing the project. Maintaining a large workforce in the middle of the desert was impossible without a reliable water supply. To solve this problem, engineers launched a parallel infrastructure project, building a freshwater canal from the Nile River to the Suez construction site. This canal became a true lifeline for the entire operation. It provided drinking water for tens of thousands of workers, supported the formation of temporary settlements along the construction corridor, and created the logistical foundation that allowed the project to continue operating in such a harsh desert environment. At the peak of construction, it is estimated that up to 400,000 workers were brought to the site to dig soil, transport materials, and widen the canal using simple hand tools. They worked under extreme heat, with limited access to drinking water, and almost no protective equipment by modern safety standards. Working conditions were physically demanding and often dangerous, especially across long stretches of open desert terrain. In 1864, when the system of forced labor was abolished under strong international pressure, the Suez construction site immediately faced a serious labor crisis. Hundreds of thousands of workers left the site almost at the same time, putting the entire project at risk of coming to a complete standstill. This sudden loss of manpower forced engineers and project leaders to urgently search for alternative solutions to keep construction moving forward. At that moment, a critical question emerged. If there were no longer hundreds of thousands of manual workers who would continue digging the canal, the engineer's answer was not to recruit more workers, but to completely change the way the project was built. A decisive turning point followed: the full mechanization of the construction site. Large numbers of steam-powered excavation machines began arriving in Egypt from Europe. These were among the first large-scale canal-digging machines ever deployed on an infrastructure project nearly 200 kilometers long. Unlike manual labor, which could remove only thin layers of soil each day, these machines could operate continuously for many hours and produce several times more output. As a result, construction progress increased significantly within a short period of time. Mechanization did not only make excavation faster, it also allowed engineers to control the shape and depth of the canal channel with much greater precision. This level of accuracy was extremely important for a maritime route stretching hundreds of kilometers and requiring a stable and consistent gradient along its entire length. Even after steam-powered excavation machines began replacing manual labor at the Suez construction site in the late 19th century, a series of major engineering challenges continued to threaten the progress of the entire project. Most of the canal route was built across loose sand layers and weak sedimentary ground. As excavation went deeper, the canal banks became highly vulnerable to collapse, especially in areas affected by strong desert winds or seasonal water level changes. This forced engineers to continuously adjust the slope geometry along both sides of the canal to ensure long-term stability, rather than treating excavation as a one-time operation that ended once digging was complete. In other sections, the construction route passed through natural depressions and lake regions, including areas that later became part of the canal system itself. In these locations, construction was not simply about removing soil. Engineers also had to carefully manage water levels in order to transform existing natural lakes into integrated sections of a continuous navigation corridor, linking the Mediterranean Sea with the Red Sea. It was the ability to solve these geological, hydraulic, and logistical problems simultaneously that allowed the Suez construction site to maintain progress under conditions that many 19th century engineers had once believed made the construction of an intercontinental maritime canal across the desert nearly impossible. When the Suez Canal officially opened in 1869, many people believed the world had just completed one of the greatest infrastructure projects in history. But in reality, that moment was only the beginning of a megastructure that has never truly been finished. Soon after the canal entered operation, the size of global ships began increasing faster than 19th century engineers had originally expected. This forced the canal to be continuously deepened, widened, and geometrically adjusted over the following decades. Without these regular upgrades, the Suez Canal would likely have become outdated after only a few generations of commercial vessels. Throughout the 20th century, the canal was closed several times due to wars and regional crises, especially after the 1956 Suez Crisis and later conflicts in the Middle East. At certain periods, traffic through the canal was interrupted for several consecutive years, turning what was once a major global shipping corridor into a strategic bottleneck in international trade. Even in the modern era, the Suez Canal continues to prove that it is a structure that can never remain unchanged. The grounding of a massive container ship in 2021 temporarily blocked the entire waterway for just a few days. But that was enough to disrupt global supply chains and push engineers to continue adjusting the canal's navigation geometry at several critical sections. For more than 150 years, the Suez Canal has functioned as a living piece of infrastructure. It has been continuously deepened, widened, and reshaped to adapt to the ever-growing size of ships in global trade. If this corridor, less than 200 kilometers long, is disrupted for just a few days, global supply chains can immediately begin to shake. That is why whenever tensions rise in the Middle East, the world once again turns its attention to the Suez Canal. But what is even more remarkable is this. After more than a century and a half of operation, the canal has never truly been finished. It continues to be deepened. It continues to be expanded. And in the future, it will very likely continue to change again and again in order to keep pace with the increasing size of the ships that humans themselves are building. So in your opinion, over the next 50 years, how much more will the Suez Canal need to change to remain the most important maritime route on the planet? Let us know your thoughts in the comments below.